Geometry and algebra are two of the fundamental pillars of mathematics. Each in its own right is a very kind of deep subject, but really the most interesting thing about them is the way they interact. So we've already looked at algebra. It's the study of arithmetic, really, the general properties of arithmetic and their consequences. Geometry is a little bit different. It feels very different when you first define it. So really geometry equals the study of position, I suppose distance, shape, and size. So that's all a little bit vague because, I mean, what do each of those things mean? What does shape even mean? And it depends on your perspective, really. But intuitively, we all kind of know what geometry means. It's the study of kind of pictures, really, right? So shapes, squares, rectangles, triangles, solid three-dimensional shapes, angles, kind of how these kind of shapes can arrange themselves. It's kind of a really important topic because it's really how we view the world visually. So geometry, as I said, is kind of very interesting in its own right. It was a subject studied in great detail by the ancient Greeks, as was algebra, but really it's the interaction between geometry and algebra which is really something which is incredibly fascinating. So let's first of all just think about kind of geometric shapes in various dimensions. So we're not going to go into any kind of fancy discussion about what dimension means. We'll just talk about the basic ones. So when I say a one-dimensional shape, it's not terribly exciting, it's just a straight line. So one-dimensional shape. This is a straight line. So let's kind of draw it, I don't know, kind of a line segment, let's call it that, right? So capital A there, that's going to denote its length. This is a line segment. A very basic thing. So one-dimensional shapes aren't terribly exciting. When we get into 2 dimensions and 3 dimensions, interesting things will happen. But before I do that, I want to point out that one of the fundamental ways that algebra interacts with geometry is the fact that we can quantify geometric shapes using numbers. And remember, studying numbers and their properties is where algebra comes from. So how do we kind of quantify numerically a one-dimensional shape? Well, I suppose its length would be a numerical quantification. So let's kind of keep track of how we quantify this in the following way. So I'm going to take a one-dimensional shape and then I'm going to numerically quantify it. So it's kind of a fancy term for assigning a number to it. So quantify numerically. Ooh. So what I mean by that is describing it in some way using a number. And the way we do that in one dimension is just length. Length is our numerical quantification of a one-dimensional shape. So length. And as a kind of a convention, if I draw a line segment, I represent its length with kind of a number sitting above it often, so that A, that's the length. So not very exciting here. Let's kind of have this. If I let me do this in a slightly different color, forgive me while I just change this to make it neater. So quantifying this numerically, it would just be the letter A. The letter A over here. Okay, not terribly profound, but very important. So this is all because of our number line, right? Our number line is a combination of a geometric object because it's a straight line, but it's also numbers, okay? When we talk about 1, 2, 3, 4, 5, minus 1, a half, all these other numbers, they're sitting on this line. So this gives us the ability to quantify a line numerically, which we call length. Now, one-dimensional shapes, pretty boring, straight lines, but in 2 dimensions things become much more interesting because we have much more interesting kind of subsets of 2-dimensional space, just a plane. So 2-dimensional shapes, where things kind of kick off. So, what 2-dimensional shapes shall we do? So there's obviously infinitely many, all sorts of polygons, stuff like that, but let's just take the most basic ones that we need to kind of understand. Rectangles is super important, obviously. So a rectangle is a 4-sided shape, often called a quadrilateral. Goodness, if I can get it to work. Often called a quadrilateral. Maybe I don't want it to do that. Give me a second. So a 4-sided shape of this form is called a rectangle. The crucial thing is all the internal angles are right angles. So 90 degrees, if we're going to use degrees. Later on, of course, we'll use radians. And again, because of its shape, it's pretty obvious that if you look at the lengths of all of the sides, opposite sides have to have the same length just by the nature of the shape. Okay, so this is called a rectangle. And there's a special case of this, of course, where if A and B are the same, if those lengths are equal, so the lengths of all 4 sides are the same, we call it a square, of course, one of our kind of absolutely fundamental shapes. So if A is equal to B, this gives a square. Very nice. That's a rectangle. Maybe I should just highlight the fact that this is a right angle in here. All of these are right angles. This is our standard notation for a right angle. Okay, so what other shapes do we have? Let's do triangles. Pretty good choice. Like I said, there's all sorts of different shapes we can do, but I just want to kind of do the most basic and pull out their most basic properties. So a triangle, let's do one like this. It's kind of a general triangle. Something like that. Okay, so again, we can label the sides. Let's label this kind of A, B there, and C. So those are going to be the lengths, going to represent the lengths just like we had for the straight line segment. With a triangle, we can kind of lay it down so one of the sides is flat if you want. So is that flat? Not quite. Let me just rotate it ever so slightly. Is that better? Can't really tell. But let me do this again. Why is it never easy? Why is it never easy? Nice, okay. So if I take this triangle and I lay it completely flat on one side, and I've got kind of 3 choices about how to do this. I can drop a line down. So I can take this and I can draw a straight line from there down to here, crossing at right angles. So if I've oriented the triangle in this way, we might call that the kind of the height of the triangle, and that length we would label as h. Okay, so this is a triangle. And of course there are various special cases of this. If 2 of the sides are equal, we say it's an isosceles triangle. If none of the sides are equal, we say it's a scalene triangle. If all of the sides are equal, so maybe that's one worth saying, if A is equal to B is equal to C, then we say this triangle is equilateral. Equal sides. Right, triangle, nice and simple. The internal angles of a triangle are interesting. A fundamental fact is that the sum of the internal angles, so the internal angles are that angle there, that angle there, that angle there. The internal angles have to be half a revolution. So in degrees, that's 180. In radians, it's pi, as we're going to see later on in the course. Okay, it's triangle. What other shapes are there completely fundamental? Circles. It's another one which is totally fundamental to everything. So it's a circle. Circle's a very interesting shape. It's different than the others in the sense that it is all points which are the same distance, if you want, from a single location. So that would give a circle like this. And the crucial thing is, if you look at the middle of this shape, it's called the center, and you draw, let me try and get that as neat as possible. Where is that? Yeah, that's good. And you draw a line to the edge. That length is always the same, and we're going to call that length r. And that length r is called the radius. The radius of the circle. So maybe I should just label this as a circle. Okay, so these are pretty fundamental shapes. There's obviously infinitely many possibilities, but these are the three that we absolutely must understand. Now, in the world of one-dimensional shapes, it's very boring, there are straight lines, and to quantify them we just use length. What about two-dimensional shapes? Well, in the world of two-dimensional shapes, the fundamental numerical quantification is going to be the area. So that's really intuitively how much space they take up in the plane, if you want. But there is also kind of a more one-dimensional concept associated to all of these, namely the perimeter. Right? So the perimeter of any shape is kind of the edge of it. Right? So these all the way around. So that's a one-dimensional thing because it's a length, or it's a line, so it has a length. So kind of numerically quantifying this, there are kind of two things that jump out at us. There is kind of the area, which is kind of the kind of space that the whole thing takes up internally, like that. But there's also the perimeter. So these are kind of two fundamental numerical quantifications of any two-dimensional shape. So yeah, let's say the two things that we need to be aware of are perimeter and area. So that's kind of the edge around, or the edge of the shape, and area. And that's how much space it takes up in the plane, if you want. Now, this is where algebra comes in, because once we've kind of labeled the lengths of the edges of these shapes, or the radius, for example, we can write down the perimeter and area as a piece of algebra. So some sort of expression involving these lengths, A, B, or C, or indeed H, or R, and it gives us an algebraic expression. So first of all, let's do the rectangle. Rectangle. What's the perimeter of a rectangle? Well, it's going to be the overall length around the outside. So that's A plus B plus A plus B. Putting all that together, simplifying a little bit, gives what? Well, the perimeter is equal to, well, 2A plus 2B. It's important with things like this not to just memorize that formula, but to understand where it's coming from. It's because A plus B plus A plus B can be rearranged to give 2A plus 2B. What about the area? Well, essentially the area of a rectangle is defined to be the product of the A and the B. So often called the kind of the length and the height, or the width and the height. So it's defined to be A times B. So the bigger A or the bigger B, the larger the area of the rectangle, which makes a lot of sense. Okay, what about the triangle? Triangle. Well, this is a bit more subtle. The perimeter is pretty obvious, isn't it? Because the perimeter is is just the sum of the lengths around the outside Okay, pretty simple. So just a, that, plus that, plus that. The area. Well, this is more difficult, especially if I had just given you A, B, and C. Then the area is a pretty subtle thing. It's not easy to work out what it is. Intuitively, you know, it's how much space it takes up, but to actually come up with a formula involving A, B, and C is not simple. However, when we have the height, this h as I drew it, that makes life much simpler. And it turns out the area is equal to the familiar expression, hopefully. It's a half of the base times the height. And that could be done with any of the heights if you want. Remember, we could take this triangle and kind of rotate it around to put a different base. It would give you a different height, but you'd have a different base. But the thing is, the area would still be the same. So if, for example, you rotated this around so that this was the base now, you'd have a different height. It would be kind of going up like that. The product of that height and b times a half would be the same thing. So it's kind of a numerical invariant if you want. Okay, so circle. This one is probably the most interesting, really. So the circle. First of all, it is a fact that if you take a circle and you take the length around the outside of the circle, so we'll talk about this a little bit later on. If you take the length around the outside of the circle and divide it by the diameter, so the diameter is the length all the way across like that, so in this case 2 times the radius, 2r. If you take that ratio, it is always the same regardless of the size of the circle. So the ratio of the outer length, the diameter, sorry, the circumference it's called, divided by the diameter, which is the length across, it's always the same number. And it's a very interesting number because it's much more complicated than it might first seem. First of all, it's bigger than 3 and less than 4. But then when you try and dig into it a bit more, well, it's a bit of a strange number because it doesn't settle in a simple location. You might think it's 3.5 maybe, but it doesn't work. It's a bit smaller than that. So basically, as you try to work out this number more and more accurately, it becomes more and more interesting, at least as a decimal. And it's pi. It's 3.14 ... So something I do want to stress is people often say that pi is infinite. That's not true. Pi is finite because it's less than 4, but it has a very interesting decimal expansion it never settles into just zeros eventually. So when people say it's infinite, they don't really mean it's infinite. They just mean it's got infinitely many non-zero numbers in its decimal expansion. Anyway, let's not get sidetracked too much. The ratio of the circle circumference to the diameter is pi. That's the definition of pi. So if anyone ever asks you what's the definition of pi, don't say 3.14 ... Say it's the ratio of the circumference to the diameter. Now, if that's true, then we can kind of rearrange that to give the following. The circumference, or the perimeter, that length, would be equal to pi multiplied by the diameter. Just rearranging that fraction. But the diameter is 2 times the radius. So taking that and rewriting it, we would end up with the perimeter is equal to 2 pi r, a familiar expression. So that's really by definition of pi. Okay. Now, much more interesting is the area. So the perimeter, or pi if you wanted, was defined essentially to be this ratio of the... Pi was defined to be the ratio of the perimeter to the diameter. So that's kind of by definition this formula. But much more interesting is the area. And it turns out the area, this is not at all obvious, is equal to pi r squared. I would imagine this was first determined by someone like Archimedes, or at least Archimedes will have had various awesome proofs of this. So pi r squared, very familiar formula. So yes, so let's just make sure we understand the notation here. This is pi. Pi, 3.14 ... Very interesting number. Okay, so obviously we could go on all day with different shapes, but these are the three I think we absolutely must need to understand completely. Something about triangles as well is there's a very nice relationship between the lengths of the triangle in a special case. So if we have a special case here where the triangle looks like the following, let's do this. So a triangle where one of the internal angles is a right angle. So if I have this, let's do A here, B here, and C here. Let's imagine I kind of move this around a little bit. Does that make sense? That orientation doesn't matter too much. In fact, no, I should keep the same. I should keep the same style. So I'll have a B there and a C there. That's called a right triangle, a right angle triangle. In this case, there is a very beautiful relationship between the lengths of the triangle, namely the length of the hypotenuse, which is this length here, the one opposite the right angle. The square of that is equal to the sum of the square of the other two sides. So that is Pythagoras' theorem, which states that b squared is equal to a squared plus c squared in this case. So this is Pythagoras. Another very important thing that is used all the time. So it's something you need to be completely familiar with. We'll see it turning up a little bit later on. Okay, so as I said, there's tons of stuff to say about two-dimensional shapes, two-dimensional geometry, but this is the stuff which is absolute bedrock. We must have this completely internalized.